Hello everyone, welcome to Lab 5. So today we're going to design microstrip antennas which are very popular because of their low profile, their ease of fabrication, and how easily they can conform to planar and non-planar surfaces. A microstrip antenna is simply a metallic patch or a metallic strip on top of a substrate and a ground plane, which can be fed with either a microstrip line or a coax cable. So their feeding is fairly simple. All right, so let's dive in. So we're going to design a microstrip line fed rectangular patch antenna, as you can see in Figure 1. We're going to design it on FR4, which has an epsilon R of 4.4 and height of 1.6 millimeters. And we want to design it at a central frequency of 2 gigahertz, and we want the S11 at 2 gigs to be less than minus 20 dB. And we also want the input impedance of the microstrip line to be 50 ohms. Okay, so the first part here is to calculate the width of the line that has 50 ohms, which you guys have done quite a bit now. So you can do that either using ADS or using one of the online calculators. So I've already done that, and I found that the width of the line has to be 3.1 millimeters. So you can go ahead and do that, or you can just make a note of it. So the width has to be 3.1 millimeters. The second part is to calculate the width and the length of the patch to resonate at 2 gigahertz. And again, you can use formulas which you can find in many antenna books, or you can go ahead and find a calculator online. So I found this calculator that you can simply put in the dielectric constant of the substrate, the height of the substrate, the frequency, and then it would give you the value for the length and width of the patch. So you can go ahead and do that. 4.4 for the dielectric constant. The height of the dielectric is 1.6 millimeters, and we want to operate at 2 gigs. So the width and the length of the patch have to be these numbers, so you can make a note of that. So the width has to be 45.61 millimeters, and the length has to be 35.42 millimeters. All right, so after you have these numbers, you can go on HFSS and design the patch. And one thing we also have to design is this inset, which allows us to match the microstrip line, which is 50 ohms, to the patch. And the idea is we are feeding the patch at a certain distance inside as opposed to at the edge, because at the edge it's not going to be 50 ohms, and that's why we need this inset. And the starting dimensions here are 2 millimeters for the width and 6 millimeters for the length. Okay, so I think we can go on an HFSS and start designing it. So I'm gonna go ahead and create a HFSS design here. So we can call this patch antenna. So the first thing we want to design is the substrate, which would be a simple box. We can call that substrate. It's going to be FR4, so you can search for FR4. It's right here, so just confirm the dielectric constant and loss tangent as was given in the lab manual. All right, so in terms of the length and the width of the substrate, of course, it would depend on the size of the patch, and it has to be slightly bigger than the patch, because the patch radiates from the fringing field, so there's got to be some substrate around the patch in order to allow for radiation. I know what the size of the patch is going to be, so I can just make the substrate slightly bigger in both length and width. So let's go ahead and do that. So I'm going to have the substrate also centered in the coordinate system, and I'm going to have the patch be directed in the minus x direction. So you'll see what I mean. All right, so position in x, we'll create a variable for the length of the substrate. we'll create a variable for the width along y, and we'll start at 0. So the length of the substrate has to, of course, include the length of the patch as well as the length of the line. So I'm going to say, let's see if 15 centimeters could be good. So we'll start with 15 and see if we need to increase it after that. The width of the substrate, it's going to include the width of the patch and be slightly bigger. So the width of the patch is 45 millimeters. So let's say we'll do 10 centimeters for the width and see if we need to increase it. So the size in X will be length of the substrate, size in Y will be the width, and then here will be the height of the substrate, which was given in the lab manual as 1.6. Okay, so Control D. All right, so we'll first design the microstrip line and then the patch. So we can use a surface for that. We can do that and give it a different color. You can see it. All right, so it has to start at plus sub L over 2. So we can do that, sub L over 2. In the Y, we can start at minus the microstrip width over 2. So that will be a variable that we're going to define. And it has to be on top of the substrate, so it'll be sub H. All right, so the width of the line, as I mentioned at the beginning of the video, it's 3.1 millimeters to get 50 ohms. And of course, we're going to confirm that with HFSS as well. So 3.1. Right, that wasn't exactly millimeters. I forgot to put millimeters. So there you go. Let's go back here. All right, so the size in X will be, so that will be the length of the line. So the length of the line, we are free to choose. So it doesn't have to be that long, but we can choose a reasonable number. So that'll be length of the line, actually minus length of the line. So it goes in the negative X direction. So you can choose something like 60 millimeters. And then the size in Y will be the width of the line. All right, so that's the microstrip line. You can call that microstrip line. Okay, and we can put the patch. We call that patch. Of course, we have to assign the surface or the sheet the correct boundary, either copper or PEC, but we'll do that after we have the patch ready. So the patch will also give that a different color so we can see it. So the patch would start at the end of the line. So that would be sub L over 2 minus the length of the line. In Y, it will have, so the width of the patch over 2. We can do minus width of the patch over 2. And in Z, that will be on the top of the substrate, so just sub H. So the width of the patch, as we just calculated, is 45.61 millimeters. The X size will be minus the length of the patch, because we want it to go in the negative X direction. And the length of the patch was 35.42 millimeters. And the size in Y is, of course, just the width of the patch. Okay. So that's what we have now. Go check the variables, make sure that everything's good. So the width is 45.61 millimeters. The length is 35.42. The width of the line is 3.1 millimeters. Height of the substrate is 1.6. Length is 15. Seems to be a bit long. So we can make that a bit shorter actually. So we can maybe 12. I think 12 centimeters should be good. And the length of the line is 60 millimeters. Okay. So now we have to make an inset, which would simply mean making some cuts around the line. So for that we can just add a rectangle on either side of the patch and just subtract that from the patch. So that one, in X, it would start at, same thing as the patch, so it would be sub L over 2 minus the length of the line. In Y, it would start at the width of the line over 2, and it would be on top of the substrate. So the size in X would be minus the length of the inset. So we'll call that inset L. And in the lab manual, I'll tell you guys to start with something like 6 millimeters. And we'll of course change that later on. And the width will be minus the width of the inset. And again, in the lab manual, I mentioned that you can start with something like 2 millimeters. And I don't know if we got the, yeah. All right, so that's the first inset. So if we just do a top view, you can see that it's just beside the microstrip line here. So we just need to copy that and have it on the other side as well. So you can just Control C and Control V, and you can have that as plus microstrip width over 2 and width of the inset. All right, so these two rectangles need to be subtracted from the patch. So if I select the patch and then select the two rectangles, and then I can subtract, and there you go. So now we have the insets created, and of course, if you go in the variables, you can see if I change this to 10, the length is changing. If I change the width to like 4, the width is changing. So just change that back to 6 and 2. All right. So and as I mentioned, the length of the patch, the length of the inset will be used to match the microstrip line to the patch. So at the ends of the patch, or at the edge of the patch, the impedance is not 50 ohms. It's actually at its maximum, and moving, feeding the patch closer to the middle of the patch can get you close to 50 ohms so that the line is matched. And we're going to find out what length of inset is best for that. And in part B, I'm also asking what other technique can be used to match the patch to the microstrip line. And that's a technique that we have used before, so I'll let you guys think about it. If you have two different real impedances that you want to match, what can you use? So that's the question. All right, so now we need to have the, well, actually, before I do that, I'm gonna assign a boundary to these sheets. So here you can do a copper boundary, but just for simplicity, I'm gonna use a perfect electric conductor. I'm gonna assign that. So we have this this boundary for the microstrip. All right, next we have to have a wave port. So the wave port will be in the YZ plane. So you can put a rectangle there. So that would be our wave port. All right, so the wave port will be, of course, at the edge of the substrate here. So the X position will be sub L over 2. Y position will be the width of the wave port over 2, and then it will start at 0. And of course, the width of the wave port, as a rule of thumb, it's 6 times the width of the line. And then here, width of the wave port. And then the height of the wave port is 6 times the height of the substrate. Oh, sub height. All right, so we have the wave port here. Also give that a different color, so it stands out. All right, and then we'll assign that as a wave port. Good. So the only thing left is to have a radiation box. So we'll create a vacuum box. So we'll call that rad box. We'll make it more transparent so we can see inside. So of course the radiation box will extend in X and Y as the same dimensions as the substrate, and in Z it will be at least lambda by 4 away from the top of the patch. So let's go ahead and do that. So we'll start at 0, and then in X it will be sub L, and Y will be sub W, and in Z it will be sub H plus at least lambda by 4 away from the top of the substrate. So since we're operating at 2 gigahertz, you can calculate lambda at 2 gigahertz, and you'll find that it's 150 millimeters. Lambda by 4 is 37.5 millimeters. So we can do something like 40 millimeters. So that's more than lambda by 4 away from the top of the patch. We can do something like that. Okay, so now we have to assign the radiation boundary to all the faces of the radiation box except the bottom of the substrate. So we press F on the keyboard, select these faces. This face, and then assign them as radiation boundaries. All right, so every face except the bottom is assigned a radiation boundary. So that's good. Next step would be to set the solution frequency and the sweeps that we need. So if you go under analysis, solution setup, to advanced. So we're only interested in frequencies from 1 to 3 for the S parameters, which is coming next. So we can set the frequency here to 3. Maximum number of passes, let's do 15. All right, let's do 20 because it needs more. Maximum delta S 0.01. Minimum number we'll do 6. Minimum converge passes. So I'm going to leave it as 1 because we'll be running some parametric sweeps, and I don't want the video to be too long. But when you guys do it, you should set this to 3 like we usually do. But for now, I'm going to leave it as 1 just for the video purposes. You do that. In terms of the sweeps, we're interested in frequencies from 1 to 3, and we can leave that as interpolating. And we're also interested in the radiation at 2, so we're going to have to add a discrete sweep at 2, but we can do that when we're done the optimization that we're going to do next. Okay, so I think we're done for that, so we can validate, make sure that there's nothing wrong, and we can simulate it. Go look at the conversions. Okay, so my conversion is done. Again, just because I have one converge pass, but you would have 3, so it might run for just a little bit longer. All right, so the first question, or the first thing that we have to plot is in part C, which is plot the impedance of the microstrip line, real and imaginary, from 1 to 3. So this is just a step to confirm that the width of the line was correct. So we can plot the port Z0 like we've done previously. So here it would just be port Z0, and we want to plot the real and imaginary. So we'll just wait until it's done. Okay, so it's done. So you can see here that we're very close to 50. We can just check here. So we're like 50.17, so it's pretty much 50. And the imaginary part is almost 0. So the impedance of the line is correct. So that's part C. Part D is to plot the S11 from 1 to 3. So we can go ahead and do that. So before I do it, just take a few seconds to think what you would expect S11 to look like. So we designed the antenna to resonate or radiate at 2 gigahertz. And if I tell you that microstrip antennas are fairly narrowband, what would you expect S11 to look like? Before we plot it, you can think about it. All right, so if you expected S11 to be low at a certain value close to 2 gigahertz, that's right. So you can see here that the point of lowest reflection, which means that the power is not coming back at this point, and if the power is not coming back to the port, it's either lost or radiated. And of course, since this is an antenna, it's radiated to free space. So that's the general shape of the S11 here. So you can see it's close to 2, but not quite. And also, it's not meeting our specifications, namely S11 at 2 gigahertz has to be less than minus 20 dB. So we need to do a bit of work here to fix it. So the first step is to adjust the length of the patch to achieve the lowest S11 at 2 gigahertz. So that's part E. So you can see here that we're very close to 2. The length of the patch is 35.42. Right here. So if you want to make the frequency bigger, we would have to make the patch shorter. So we have to make the length of the patch slightly shorter. So for that, we can run an optimization, but since we're already very close, we can just run a parametric sweep with some values just smaller than 35 millimeters or smaller than 35.4 millimeters, and then see what value gives us the lowest S11 at 2. So we can add an optometric parametric sweep, and we'll do that for length of the patch. So right now it's at 35.42. We know that we want the frequency to go higher, which means it has to be less than 35.42. So we can do something like 35 to 35.4 in steps of 0.1. Let's see if that gives us the right numbers. There's going to be 5 simulations, and if you have the HFSS configured to run multiple simulations in parallel, which we've done in the previous lab, so your HFSS should already be set to do that. This shouldn't take a long time. Okay, so we have a parametric sweep for the length here, so we can go ahead and run that. And just a note for microstrip antennas or like the rectangular microstrip patch antenna, the width and the length both affect the frequency, but the length has the biggest effect on the frequency, and that's why I decided to adjust that instead of both the length and the width. And if you look at the equations in the online calculator, these equations they tell you the effect of like the length and the width on the frequency. And they're, of course, analytical equations. And as we have discussed this before, these are the kind of equations that ADS would use, but HFSS is solving Maxwell's equations exactly. And you can see the equations, they provided us with a very close answer. It just needs to be tweaked a little bit. Okay, so all 5 simulations are running in parallel. It's good. So I'm just gonna create a new report, and instead of just the nominal value of the patch, I'm going to use all values. Of course, they are still running, so they're not available, but we can just create a new report and wait for them to be plotted here. So you can see the results are starting to appear, but you should wait until the simulation is finished for the final results. So these are still not the final results of the simulation. Yeah, so just one simulation is left. So you can already see that we have a certain length of the patch that can give us the correct point that we need. So seems either 35.1 or 35.2. I would say 35.2 is the point that we're looking for. So if I go here and I change the length to 35.2, this plot should be correct. Yeah. So the S11 plot here is is selecting the nominal value, and the nominal value is the one that you have in the properties of the variables. So right now at 35.2, we have around minus 13 dB at 2 gigahertz. So we're getting close. Okay, so the next specification that we have to meet is the S11 has to be less than minus 20 at 2 gigahertz. And this, as I mentioned before, can be achieved by adjusting the length of the inset. So right now the inset is 6 millimeters, and it actually needs to be made longer in order to improve the match. And the reason is, like I mentioned, at the edge of the patch, the impedance is at its highest. And for these patches, it's around maybe 300 ohms. And as you get closer to the center, the impedance goes down. And at the center of the patch, the impedance is actually 0. So it's somewhere between the edge and the center where the impedance of the patch is 50 ohms. And that's what we're trying to achieve. So this simulation is done, and we have a good length of the patch, which is 35.2. So now we can just disable this parametric sweep, and we'll add another one for the length of the inset. So we'll add another parametric sweep for length of the insets. Right now it's 6 millimeters, and it has to be made longer than 6. So I'll start at 6 and maybe end at 10 in steps of 1 millimeter, and we'll see what we get. So we have same thing as before, 5 points. So we can run that. So what I just did is part F, so adjusting the length of the inset to achieve S11 less than minus 20 dB at F0. And while this is running, we can go ahead and add a discrete sweep for the next part. So the next part, we're going to plot the radiation pattern at 2 gigahertz. And as you know, for any field results, we need to have a discrete sweep. So we can add a discrete sweep at 2 gigs, and we just need 1 point, so a single point, and we'll make sure to save the fields. And we also need to have a far field setup, as you guys know, for the radiation pattern. So I'm going to go ahead and add that as well. So far field setup, infinite sphere, we'll do 5 from 0, 360 in steps of, we can leave it as steps of 2, that's fine. And theta from minus 180 to 180, and we'll do in steps of 1. Okay, so we'll just wait for this parametric sweep to be finished. Can also so for the patch length, we'll set that to 35.2, and we'll plot everything for the inset. So we'll go new report. All right, so everything we see here will be for the length of the patch that we want, and variable inset dimensions for length. And again, any result that you see when the simulation is not done, it's not correct. So you'll have to wait until the simulation is done. By the way, if you're watching the video, you can just fast forward to the point where the simulation is done. I just don't have time to edit the video, so you can just fast forward if you want. I probably wouldn't be saying anything important until the results are good to go. So the results seem to be coming along. So 10 millimeter of inset seems to be the best one. So we get around minus 25 dB at 2 gigahertz. So I think that's what we're going to stick with. This one is still calculating, but I suspect 10 is the best one, and you might even get better if you go 11 or 12. But since this one meets our specs, we can just go ahead with that. So I'm just going to change the length here to 10. And this plot, which is the nominal, this is the one that we're after. All right, so we have now finished part F. So we found the length of the inset that achieves our specs, and if I add a marker here, you can see at 2 gigahertz we're at minus 25. So we're good. Okay, so the next part is to plot the radiation pattern at 2, and that's why I had I added the discrete frequency point. I don't know if I can run it while this is running. I'll try that. Yeah, that's okay. I can run the discrete sweep. Yeah, might have to wait for that to finish. Okay, so we'll run that discrete sweep. And for part G, we want to plot the 3D radiation pattern at 2 gigahertz. So we can get that ready. So far field 3D polar plot. We want to plot for all phi and all theta. We want to plot that at sweep 1, which frequency is 2 gigs. And the length of the answer is 10. That's good. And we want to plot the total gain in dB. So we can have that plot ready. So there's no field because the results are not done yet. And for part H, we want to plot the co and cross polarized gains in the phi 90 plane at f0. As you guys know from the previous lab, we can look at two principal cuts. We can have like a phi 0 cut or a phi 90 cut. For the patch, the phi 90 cut is going to be enough to describe the radiation performance. So we're going to plot the co and cross polarized gains in the YZ plane. One thing I forgot to mention is in part F, I'm asking for the fractional bandwidth. In the previous labs, I was asking about the bandwidth, which is simply the minus 10 dB bandwidth is the frequency difference between these 2 points, minus 10 on this side, minus 10 on the other side. The fractional bandwidth is another definition of bandwidth that's used in antenna engineering. So I'll let you guys Google that and see what it means. And the question is asking about the fractional bandwidth at 2 gigahertz or around 2 gigahertz. Right, so the simulation is close to being done. All right, so let's look at the 3D radiation pattern. So that's what it looks like. So as you can see, there's the gain is low, of course, below the patch because it's a ground plane, and it has the highest gain in the positive Z direction. And again, that's the reason why I had it in the XY plane, so that the radiation is maximum in Z. That's usually how antennas are designed. The maximum radiation is usually designed to be in the positive Z direction. All right, so now we wanna look at the radiation pattern cut in the phi 90 plane. So to do that, we can go under far field. You can go rectangular plot. So co and cross polarized gains, as you guys remember, phi and theta. One of them is co, one of them is cross, and we'll see which one is in a second. Of course, we're going to plot that at 2, and we want to plot it in phi 90. And the length of the patch, there should only be 1. Yeah. Also, the answer, there should only be 1, which are the ones that we just found. Okay, so there you go. So gain phi is the copolarized gain, gain theta is the cross-polarized gain, and you can see that from the patch here. So if I were to ask you what's the polarization of the patch based on this plot, the fact that gain phi is the copolarized, given that of course it's in the phi 90 plane, or actually if you just look at this, what's the polarization of the patch? So think about that for a second. So the polarization of the patch, so the current is flowing in this direction, which means the electric field is also in this direction. So the polarization is in in the x direction. So the patch is polarized in the x direction. If you're plotting the gain in the YZ plane, gain phi will be along the co-polarized direction. Gain theta will be cross-polarized. So gain theta will be along the y-axis. Gain phi will be along the x-axis. So gain phi is copolarized. It's in the same direction as the E field. Gain theta is cross-polarized. It's 90 degrees with respect to that. Okay, so that's part H, and that's the end of the first section. It's right here, and of course the broadside gain is the maximum gain here, which is 1.8 dB. All right, so first section is done. Now we're on to the second design, which is a 2-element microstrip antenna array, or I should say a multi-element microstrip antenna array. So antenna arrays are really useful because they allow us to control the radiation pattern in ways that a single element does not allow. For example, if you look at this patch, there's nothing that we can really do to, for example, change the direction of radiation to a different angle. We cannot control the beam width of the design much. So for example, here there is a certain, if you guys remember, 3 dB beam width. This one is fairly wide. But if we want to make it narrower, we can not easily achieve that with a single element. We can control it a little bit, but a single element does not provide us a lot of control over the radiation pattern. Now what they found is if you have multiple elements radiating simultaneously, you can add a lot of degrees of freedom to control the radiation pattern, and that's what arrays are. Arrays are multiple elements, multiple antenna elements that are fed or excited at the same time. They can be excited with different amplitudes, different phases, in order to control the radiation characteristics. So I encourage you guys to read that section in the lab manual. So it's section 3, and I will try to summarize it here in the video as well. The basic idea is what they found is the gain of an array of elements, or actually the field of an array of elements is described by the field of a single element multiplied by something called an array factor. And the array factor has the information on the arrangement of the elements and the amplitude and phase differences between the excitations. So if you have the field of a single element, you just multiply that by the array factor, which describes how the elements are arranged and are fed, and then you get the field of the total array. For a uniform amplitude excitation, the array factor is given by equation 2 in the lab manual. So it takes into account the number of elements, which is n, and it has an expression psi, which is the most important expression in this equation. Psi equals to kd sine theta plus beta, where k is the phase constant. It's equal to 2 pi over lambda. Theta is the angle with respect to the z-axis, so that's the angle measured from the z-axis, as you guys know. And beta is the phase progression between the elements, so it tells you how much phase difference exists between the antenna elements that you're feeding. And the values that you have control over are beta, which is the phase progression, and d, which is the separation between the elements. By controlling beta and d, you can control the maximum angle of radiation, which is theta. So the idea is you want to maximize the radiation by maximizing the array factor. And if you guys look at equation 2, if you do some limits analysis, you can see that in order to maximize equation 2, the value of psi has to be 0. So kd sine theta plus beta has to be 0. So in order to maximize the radiation, you will set this to 0. You will set the angle that you want to maximize the radiation at, which is the angle theta. And then you have the freedom to choose d and the phase progression. And the limitation on d is that it has to be less than lambda in order to avoid grating lobes, which are lobes that can appear in the radiation pattern if the elements are too far apart. Okay, so like I said, I encourage you guys to read that in the lab manual or find it in an antenna textbooks. Arrays are are fairly involved, and I'm sure the professor is gonna talk about that in class. Okay, so let's dig into it. Section 3.1. We want to have a broadside radiation using a 2-element array. So lucky for you guys, for everything in this section, we're going to use the same patch that we just designed. So the patch that we have in this design, that's all you need. So you just need to have different phase excitations and put them in the same project. So it's fairly straightforward. All right, so section 3.1 is to design a 2-element array of the patch in section 2, which is the patch that we just designed, to radiate at broadside, and assume the two patches are fed with equal amplitude and are separated by a distance of d 0.5 lambda. All right, so the first question is to calculate the phase progression needed to achieve broadside radiation. Maybe in here I should go to the lab manual. All right, so calculate the phase progression needed to achieve broadside radiation. So like I mentioned, the most important expression in the array factor is the value of psi here, which has to be 0 in order to maximize the radiation. And if psi has to be 0, which is here, you're free to choose whatever angle you want to radiate at. You will set the distance to a certain value, and then you can calculate the phase progression, or you can set the phase progression and then calculate the separation, but it's usually easier to calculate or set the separation to a certain value and then calculate the phase progression. All right, so for broadside radiation, what's the value of theta? So theta will be 0 for broadside. So we have kd times 0, which is 0, plus beta equals 0. So what's the value of beta? All right, beta has to be 0. So that's it. So part A, beta has to be 0 in order to achieve broadside radiation. Part B is to design an array on HFSS, or design the 2-element array and plot the co and cross polarized gains and compare with the single element. Okay, so like I said, you guys are really lucky. I can save that. All you have to do is just duplicate the patch design and excite them with 2 wave ports. So I'm just gonna go ahead and copy that. We'll call it 2-element. So the part that we need to copy is the patch and the wave port. So we'll just copy the patch, the line, and the wave port. So I'm gonna Control C, Control V, and I'm just gonna right click and then move them a certain distance away, and I'll figure this out in a second. All right, so we just need to move them. So I should mention that in this case we're designing a 1D array, right? So they will be in the same along one line, is what I meant to say. And in this case we want them to be along the y-axis. So 0 for x, y we want them to be a distance d away, and as you guys saw in the lab manual, d is 0.5 lambda, and since they're radiating at 2 gigahertz, 0.5 lambda at 2 is 0.5 times 150 millimeters, so it will be 75 millimeters. But of course we can just create a variable. You can call it dist, and there's no variation in z. And here this will be 75 millimeters. And I'm just going to copy that and do it for all of the other ones. Oh, and copy that right. There you go. All right, so we have the other patch here, and now we just need to extend the substrate and the air box to cover it. Actually, before I do that, maybe I will assign those as pecs. And assign this as another wave port. And there's something that we have to do in the wave ports, which I'll mention in a second, something that we have to take care of. But for now, I will just do that. Okay, so the substrate has to be extended. So the width has to be made bigger. So let's try width times 2, maybe a little too big. 1.5 maybe, a little too small. Yeah, maybe 1.7. And we'll do the same thing for the air box. Okay, so there you go. That's your two element array. So now there are two wave ports, and we want to excite two wave ports at the same time. That's what we want to do, right? So if you go under excitation, edit sources, you can see which ports are being excited, and more importantly, you can see what the phase of the excitation is. So this phase would be important when you guys go to part 3.3, where there is actually going to be a phase progression. So right now, for broadside, the phase is 0, which means there is no phase progression between the elements. All elements will be excited with the same phase. So 0 and 0 is good. 10 and 10, 100 and 100, as long as the phase is the same, or there's no phase difference between the ports, it will radiate a broadside. So right now, there's only one port excited, so of course we have to excite the other one as well. So we'll put that as 1 watt. And the phase difference is 0. So that's where the phase progression would go into play in part 3.3 when you guys design it. So just keep that in mind. Okay, so now we have the two ports excited. But one thing that you actually have to take care of when you're designing arrays or any excitations or feeds on HFSS where you're using wave ports, and if you want them to be excited the same way, is you need to define the integration line. So everything that we've done so far with wave ports, we did not assign an integration line. We sort of let HFSS kind of randomly decide how the excitation is going to go from the point of view of the wave port. But you actually need to take care of that if you're doing something like an array where you need them to be excited the same way. And for that reason, we have to assign an integration line to the wave port. And that's what we're going to do now. So if you go under the wave ports, one thing that we did not do is assign an integration line. We just left it as none. But now we actually have to assign an integration line, which I don't know if I mentioned this before. It's just the direction of the voltage of the mode that you're exciting. So here it's more of a TEM mode, quasi TEM mode, but we can assign a direction to where the field is, the voltage is going to be. So we can go ahead and do that, and it has to be the same for both of them. Right, so if you do a new line, I'm just going to zoom in here just so that you can see. So what I'm going to do is I'm going to go from the middle of the port here to the top of the port. So I'm just going to assign the integration line this way. And that's it. We'll press OK. And I will do the same thing for the other port. So that's a very key point. Don't forget to do that. You have to have the integration line assigned the same way between the ports. Otherwise, your array may not work. So I'm just going to do a new line. Zoom in on this one. And then go from the middle to top here. Say OK. All right, so wave ports, integration lines are all going the same way. You have the two patches. They are separated by a distance of 75 millimeters, which is lambda by 2, as specified in the question. You can also check. It's always the center to center separation. That's important. So if you go from the center to the center here, you should measure, as you can see in the top of the screen, 75 millimeters, just to confirm. All right, so we have, just make sure the boundary is good. So we have the first pack, second pack, we have a radiation boundary. We have the two wave ports. And over here, we're not interested in the S parameters because we know what they are. We've already done it. So we can just delete this interpolating sweep. It's not needed. We can just disable it. And we can also disable this parametric sweep since we already optimized the patch. Okay, so we should be good to go. I'm just going to validate, make sure everything is good. All right, so we'll analyze that. So while this is running, um, I'm going to talk to you guys about the next two parts. So at the end of this will be the end of the demo. And you guys will work on part 3.2, which is broadside radiation using 3 elements. So this will be the exact same thing that we just did here, except that you will just add another element. So there will be 3 excitations. And you will look at the radiation and see what it looks like. Part 3.3, this will be an off broadside radiation. So your phase progression will not be 0 anymore. So you'll have to calculate beta based on psi equals 0 that we just talked about. And you'll have to find what phase progression you need to achieve a radiation at 10 degrees and a radiation at minus 10 degrees. And the phase progression, it's going to be for the 3 element array. So if the phase progression, let's say, I'm just going to go here to show an example. So if you need a phase progression, you can set the first one at 0. The second one is going to be 0 plus 1 phase progression. The third one will be 0 plus 2 phase progressions. Right? So if the phase progression is, let's say, 50 degrees. The first one will be 0, the second will be 50, the third will be 100. So that's what the phase progression means. And so you'll do that for part 3.3. And I think other than that, the report is fairly straightforward. So everything is in the report guidelines. In the discussion, I want you guys to discuss feeding techniques for antenna arrays. So right now, or in this HPhysics design, this is a fairly simplistic view of how arrays are fed. We just have 2-wave ports. We can decide what phase or what magnitude we want to feed the ports. But of course, in real life, you're feeding it with either like microstrip lines that are dividing the power, or phase shifters that achieve this phase progression that we just talked about. So I want you guys to research a little bit into how arrays are fed in real life, and maybe provide some examples, because arrays can get fairly big. You can have 50 element array, and the feeding can be quite complicated. And I want you guys to just provide a summary of how this is done in fabrication. It seems like we're getting close, maybe. Let's look at that. All right, so we don't need this port impedance. We don't need the S parameters. We'll leave the 3D plot, which I don't ask about, but we can just take a look at that. Okay, so let's take a look at the gain. So one thing about arrays is that they can be used to enhance the gain, right? So do you expect the gain to be higher or lower than before? So if you guys expected the gain to be higher, that would be correct. So you can see here that the radiation pattern was more like squished in from both sides. So the 3 dB beam width went down and the gain went up, which is something you would expect from antenna arrays. And of course, the most important thing is that it's radiating at broadside. So if you look at this one, you can see that it's exactly radiating where we would expect it to radiate. It's broadside. The beam is narrower because of the addition of the second element. Just to show you guys how the phase progression can affect the direction, if I just go in here and I change the phase progression, one thing about HFSS is once you run the simulation and you're changing the phase of the wave port, you don't need to rerun. It will automatically recalculate everything. So if I introduce a, let's say 20 degrees phase progression, let's see how that affects the radiation. I'm going to take a second to calculate. So you can see here that the maximum of the beam shifted slightly in towards the left. And if I add, not this one, if I do like minus 40, let me just recalculate that. You can see the beam shifts a little bit towards the right. So that's how phase progression can affect the direction of the beam, and that's why arrays are very, very useful as opposed to a single element, because the single element you're stuck with whatever direction of radiation the antenna has. The array gives you a lot more freedom by controlling this phase progression between the elements. You can control the direction of radiation, and of course the more elements you have, the narrower this beam is going to get. So you can get very narrow beams that have a very well-defined maximum direction. Like here you can see it's still high at broadside, but because we're only using two elements. So the last thing I just showed is not part of the lab manual. I just want to show you guys when you do it in 3.3, where there is going to be a phase progression, how you can do it. Okay, let's switch that back to 0, so I don't confuse myself. Okay, so that's the end of the demo. And 3.2 and 3.3 are for you guys to work on. And if you have any questions, I will be available during the lab time as usual. All right, I will see you during the lab. Take care.